So perhaps if you've been watching the screen there, if you came for any of those other talks, come back at a future event. Tonight is about particle physics, Fermilab, computing, and the frontiers of physics. So good evening, ladies and gentlemen, young scientists and engineers, and a special welcome to those trillions of subatomic particles that just passed through your body. Goodbye, here comes the next bunch. So seriously though, thank you for coming out tonight, and thank you to our hosts at Harold Washington Center and C2ST for this opportunity to share the story of Fermilab. We're celebrating our 50th anniversary this year. But first, let me introduce myself. So, as Charlie indicated, my name is Tim Meyer. I'm the Chief Operating Officer at Fermi National Accelerator Laboratory, otherwise known as Fermilab. What is a COO? If you go to Wikipedia and you look up COO, it says, coo, the sound a pigeon makes. So I tell my family that my job is to go to all the meetings and read all the emails that my director deleted. But let me say something about Fermilab before we turn to my more talented colleagues. So what is Fermilab? We're a national laboratory supported by the Department of Energy, one of a family of 17 laboratories across the country who have been around for decades in pursuit of pushing science and technology to help improve the human condition. Fermilab has an annual budget of about $400 million, which sounds like a lot, but we employ 2,000 people and maintain a 10-square-mile campus. When you think about particle physics, you might wonder, why do we actually invest in science? Why is it a good thing for the public taxpayer to invest in science? And at Fermilab and in other parts of the government, we believe in a triple bottom line, not the one in terms of people, planet, and profit, but in terms of advancing knowledge through discoveries, creating leaders by inspiring the next generation to take up training or careers in science, technology, engineering, arts, or mathematics, and by advancing economic growth. As Charlie mentioned, one of the things we do for science is to actually help unveil new technologies that might have an impact later on. So before we let my charming colleagues amaze you, let me say something about Fermilab's next 50 years. As some of you who have celebrated a 50th birthday recognize, we've emerged from a midlife crisis. We now have a high-fiber diet. We did not, however, buy a motorcycle or go to Hollywood. We found a new future that will actually take us to the next 50 years. And that new future is about doing for neutrinos what CERN has done for the Higgs boson. So that may sound a little cryptic right now, but by the end of tonight's session, you'll have a better glimpse of what Fermilab hopes to accomplish for the global scientific community, bringing the world together to do some amazing science. Now, because everyone likes to go to the movies, I'm going to show you a 90-second short summary of this new future for Fermilab, and then we'll get into some of the different avenues that we're actually pushing forward. So with that, I will launch into a short film.
This is Fermilab, a Department of Energy national laboratory near Chicago. It's the starting place for the deep underground neutrino experiment, DUNE, powered by the Long Baseline Neutrino Facility, LBNF. The experiment begins with Fermilab's accelerator complex, which moves protons close to the speed of light. It's all part of an effort by more than 1,000 scientists from around the world to figure out how tiny particles called neutrinos work, and what role they play in the evolution of our universe. Neutrinos are the most abundant matter particles in the cosmos, but very hard to catch. Trillions stream through you every second without leaving a trace. At LBNF, the beam of protons will smash into a target, creating the most intense beam of neutrinos in the world. Scientists will collect data to measure properties of neutrinos close to the source and again far away. Neutrinos change as they travel, so scientists are sending them straight through 1,300 kilometers of rock toward the DUNE detectors at the Sanford Underground Research Facility in South Dakota. The detectors can also look for the birth of neutron stars and black holes by catching neutrinos from exploding stars. The 1.5-kilometer deep detectors will be filled with 70,000 tons of liquid argon, making them the largest neutrino detectors in the world. As neutrinos interact with the cold liquid, they create a shower of other particles and light. Those particle tracks are then picked up by electronics and transmitted as data to the surface. The information will be analyzed by scientists at collaborating institutions in countries around the world. They'll use this data to solve unanswered questions about neutrinos and maybe even figure out why matter exists. Things like planets, stars, and even you.
Thank you. So tonight what we'll hear about is some of the different elements that go into that new project. So tonight's session is about 3 frontiers of physics, showcased in that video, where Fermilab is a pioneer, part cowboy, cowgirl, part explorer, and part just sleeping and tense, wondering when the coffee will taste better as we look up at the marvelous night sky. So tonight we'll have 3 speakers. We'll have a panel discussion at the conclusion. So I'd ask to invite you to write down some of your best questions, and I'll have a chance to take those from the audience at the conclusion of our 3 talks. Our first speaker is Oliver Olikuch. When not rewriting the software that controls the World Bank during a long plane ride to Geneva, Ollie does particle physics in pursuit of the Higgs boson and all that lies beyond. At a cocktail party, Ollie is the guy who holds the table steady while you're dancing on it. But to give you a sense of his background, he's a scientist at Fermilab. He earned his PhD in particle physics at the University of Hamburg and worked at DAISY in Germany. He's a member of the CMS collaboration at the Large Hadron Collider at CERN in Geneva, and his research is focusing on physics beyond the standard model. He has an intimate knowledge of large-scale computing solutions to analyze multi-petabyte data sets in distributed computing infrastructures of 100,000 cores. So Ollie, over to you, please.
All right, great. Hi everyone. So everyone calls me Ollie, so please do that as well. I'm a scientist at Fermilab, and we're starting with the wrong slide. Here we go. That's my first slide. So I'm a scientist, and I'm also a computing expert. And computing is a very integral part of everything we do in particle physics. And it will be one of the key things we have to really solve for the new neutrino experiments, because they will also produce enormous amounts of data that we have to analyze. So why are we doing this? Well, I'm getting up every day because these are the questions that really bug me, that I really want to answer. And those are really big questions. It's about the universe. It's about what is the universe made of, how did the universe form, and what is the future of the universe. And these are very abstract questions, but to actually answer these, or to get close to an answer, we have to do a lot of technical and also computational innovation to get this solved. So I want to start a little bit with particle physics, because I thought a little bit of introduction would be nice. So if we think about particle physics, it's really about the smallest and smallest essentially we're built of. You can think about that like a Lego toolbox. I mean, everyone knows Lego, and this is what we're all made of. So if you start here at something that we still can grasp, like a crystal, you go from a molecule and an atom to finer and finer structures till you end up at the elementary scale. Here you see an electron and a quark. These are the elementary particles that form us. And here I have a list of all of them, including the force particles in the end. We have 12, we have 6 quarks, we have the electron, which we all know, and its sister particles, and here are the neutrinos, and these are the particles that we're interested in at Fermilab next. So all of this builds up all the matter, but we need forces to keep everything together and to interact with each other, and we have 4. The first one you also know best, that's the electromagnetic force. Here we have an exchange particle, which is the photon, which is kind of the wave-particle duality we always talk about. The next force is the weak force, represented by some bosons, which are called W and Z. But the weak force essentially is radioactivity. So if you want to think about it in very simple terms, it's radioactivity. The next one is the strong force, and this is very important because this one binds the quarks in, for example, the proton. And this means you cannot really see quarks on their own. You need large accelerators to actually make them visible. And that's what we do. And then there's gravity. And gravity, we don't understand at all. It doesn't fit into our normal theory. It does not even come close to it. And this is one of the big puzzles we're still trying to solve. So this is kind of a quick rundown of particle physics, of what particle physics is about. And this is what the scientist sees. It is not very glamorous. It is not something that immediately pops out. It is essentially a plot. It is a distribution of some properties, and from that we do physics. What you see here are key features, though. You see in black those dots. Those are individual collisions that we have recorded and analyzed. And in blue, you see here, this is our simulation, which is taking everything we know about nature, know about particle physics, and putting it in a mathematical construct and simulating what we're seeing in the detectors. And then you see something like this, that over time you collect more data and your simulation, so your theory describes it well, but there's something that's not really fitting, right? You can see here these events, these collisions that are here, they don't fit with the theory. So we have to do something new. We go to our theory friends and we ask them, so what's happening? And they have an idea, and we check that. And this here, this peak, is actually the Higgs boson. So this was the discovery we announced in 2012, and it fits very well. So we're very happy about that. But this also means that now we have to go on and look for the next thing that doesn't really fit with the theory. So what I'm doing is I'm working for the Large Hadron Collider, which is in Geneva, Switzerland. And you see that we're zooming into Geneva in some moment. It is a very big machine. It is actually larger than the Fermilab site. It has a circumference of 27 kilometers. And I'm one of, I think, about 10,000 physicists and a lot more engineers and support staff that work on the Large Hadron Collider. You see here the ring. You see 4 big experiments that are actually 50 to 175 meters below ground. And here, this is CMS. This is one of the 4 experiments. That's, of course, the best experiment because I'm working on it. And what we do is, in this ring, we are accelerating protons. And these protons are traveling at enormous speed. And I never can manage to get you all the 9s behind, but it's really almost the speed of light. And what we do is we collide them. We collide them in the detectors. You see 11,000 turns per second, so it's really, really fast. And when they collide in the detectors, you see this. This is one of the detectors. Particles come from left and right, and here they collide. So what you see is not the actual collision, but everything that was produced. And these things we have to measure, these things we have to record, digitize, and analyze later. And we're doing this a lot, 600 million collisions every second we can record and do physics with. And every collision is from up to half a megabyte to a megabyte. So what we did is we build sophisticated systems to really get to what we're interested in, because 600 million is too much. So what we do is we have so-called trigger systems. These trigger systems look at the information in the detector very, very fast and can really select what we are interested in from what is not very interesting. And the reduction factor is enormous. We then feed the first reduced data, which is still 100 gigabytes per second, that go into the first trigger farms. Those are large computing farms you maybe know from Google or Facebook. And here we're continuing to filter these. And then we take about 1 in every million, something like this. So we're about 1 kilohertz output. This then, you see here that only some of these events get further processed. They are collected from all 4 experiments and sent to the big computing center at CERN, where we do the first pass reconstruction. Because it's like a car accident. You come after the accident, you see some skid marks on the road, and you have to reconstruct what happened. And this is what we're doing. This is the first stage. Here we're going to reconstruct everything, and we put some stuff on long-term storage, there's tape. And then we do the first really reconstruction pass. We have a lot of compute power there. It's never enough, you can imagine, but it's sufficient to really do, and it was sufficient to find the Higgs boson. So what we do then is we are trying to give access to all the 10,000 physicists. And they are not all in Geneva, Switzerland. They are distributed across the world. So what we did is we moved the computing to the next stage, which is called the grid. And the grid is essentially a large scientific computing infrastructure that everyone can use. So we're distributing the data, and of CMS data, the one experiment I'm on, about 40% comes to Fermilab, because Fermilab is one of our big regional centers here in the US. So you see, those are very strong transatlantic networks. We have a lot of sites, about 140 different computing centers work with LHC data, and this will be similar to what we will see then for DO. So just to give you an idea of how big the data actually is, this is something from 2013 that Wired did. You see here, this is 1 year of all business emails. At that point, it was 3 exabytes, or 3,000 petabytes. The CMS experiment in that year took about 20 petabytes of data. Last year, this year is not over, last year we did 45. So you see this all grows bigger and bigger. You see here, this is the content uploaded to Facebook in each year. That year was 180 petabytes. I guess now it's a factor of 10. Google search index is 100 petabytes. I would also estimate that today it's a factor of 10. So you see here, this is kind of puts us into relation to what we do. But you clearly then ask, so what is a petabyte? Well, you know what a gigabyte is, right? A gigabyte is about 7 minutes of HD TV video. A DVD has 4.7 gigabytes, so that's what we still know. A petabyte is, those are very nice things. A petabyte is 20 million 4-drawer filing cabinets of text. A petabyte is 13 years of HD TV. 1.5 petabyte is the size of 10 billion photos on Facebook. So it's a day, essentially, of cat photos. 20 petabytes is the amount of data processed by Google per day. That's also a lot. But I think this one is the best we can relate to. 50 petabyte is the entire written works of mankind from the beginning of recorded history in all languages. So essentially, last year, CMS alone took almost everything that was written by man in 1 year. So if you think about that, you need a lot of computing. This is kind of an overview what we do at Fermilab. You need a lot of CPU. You need a lot of tape to store it. You need a disk. I mean, these are all things you possibly know from home, from your home computer or from your work computer. We have, though, a lot of very strong networks, and they are a lot stronger than what you are used to at home. In transatlantic, we can transfer a DVD in 1.5 seconds. So this is really needed to distribute all the data out. The future is here. The future is going commercial. We're going to rent computers from Google, from Amazon, and we're going to use the big supercomputers of the US at the national labs and the NSF foundations. And you see here that we are going to participate in exascale computing in the next years. So let me finish by saying, so this was a quick overview from this is the collision, this is what we're actually doing, this is the physics, to the discovery plot of the Higgs boson, or later news about the neutrinos. Thank you.
Thank you, Ollie. As I say, it's all about the data. To give you a taste of the big science, I want to introduce you to Brian Nord. Part Stephen Colbert, part Brian Greene, and every bit Leon Letterman, Brian is an astrophysicist, comedian, teacher, and all-around mentor. He works both for Fermilab and the University of Chicago, and therefore knows about the commute across the suburbs, because no one place could hold him. If we continue the cocktail party analogy, Brian is the guy who will bring you the Red Bull without the vodka at the end of the night in exchange for you pronouncing one Greek letter properly. Brian Knorr received his PhD in physics at the University of Michigan and now works as an associate scientist, focusing on the dark energy survey and the application of artificial intelligence to our biggest questions in astrophysics. A few times per year, he travels to Chile to observe for the Dark Energy Survey on the Blanco Telescope at the Cerro Tololo Inter-American Observatory or the Gemini South Telescope. Brian endeavors to express experiences in science through art, like large-scale visualizations of the cosmos and astrophotography. Through these and other mechanisms, he engages with the public on science and advocates for diversity and inclusion in science, technology, engineering, and mathematics. Brian.
Good evening. Let's turn this guy on. Thank you, Tim. Thank you to C2ST. It's a pleasure to be here. Just so you know, Fermilab doesn't have an official uniform, but Ollie and I have the unofficial brown jacket and jean short and jean pants. Just talk to us afterwards. We can tell you where to get those that nice apparel, and you can have a little lab coat of your own. Thank you for mentioning the astrophotography, Tim. That brings me actually just to this image, which connects a lot of things in the world for me. What you're seeing here, let me restart this, if I can. So what you're seeing here is the Milky Way set to the west, and then in the middle there as it comes up, let me point to it for you. So this is a large telescope that is about 10 stories high, and then again it rises to the east. So this is a time lapse that I took a couple years ago while observing at Gemini South. So tonight I want to tell you the two stories that come together in this video. It's the story of how our universe came to be and what it's actually made of. It's not, it's made of particles and stuff, sure, but it's also made of these other crazier potential things. And I want to tell you where I go. I want to give you a glimpse of where I go to actually get data so we can learn more about that. And if you do tweet, feel free to do the Twitter. You don't have to have your phone off during my presentation. I am Star Nord because I love comic books. If you're a comic book fan, you're going to get that immediately. So what is the overall story here? So the story is the universe was born about 14 billion years ago, and it's been expanding ever since. So that's one half of the challenge, is one half of the thing that we're going to talk about tonight, that there's some expansion. We don't know why it started, but we do know that it has been expanding for 14 billion years. And that's, what you can see here is that the shape of this curve. And during that expansion, things agglomerated together. So things that had mass came together through gravity. So for our entire existence, we have been experiencing this grand cosmic tug of war that, when we look at it, it tells us about our past, and it also will help us predict our future as a small little piece of species that sits out in the middle of the universe. This is what we have to look forward to out here into the future. So what does the universe look like through the eyes of an astrophysicist? Well, it's sort of all full of stars, and I guess that has to be true because we can only see light. But it's more than that. It's more than just stars. Okay. So most of us like to think of this place as home. When I was in high school, one of the reasons I got into physics was because I wanted to maybe leave this place, but I'm good for now. This is an artist's rendition, of course, because we've never sent a satellite far enough out of the galaxy to actually look at our galaxy. But this is something like what our Milky Way looks like. And there's our sun sitting in the suburbs. It's no special place, really. So what we see here is light. And everything that interacts with, emits, absorbs light, us, robots, atoms, the sun, horseheads, Iron Man, all those things, that's only a small fraction, actually, of what makes up the universe. I just want to repeat that. 5% of the universe is made up of stuff that we can see directly. 5%. So what's the rest of it made up of? So if you look at this galaxy, you can't see it here. I don't have a video of it doing a thing, but the galaxy is actually spinning. And as something spins, you think of an ice skater, or you think of if you hold a ball on a string, as you spin that, if you let go, if there's nothing to hold the ball to the end, then it's going to go flying. So similarly with gravity, gravity is helping to hold this thing together. But if you look at it the way that Vera Rubin looked at it, she was an astrophysicist, an amazing astrophysicist who passed away last year, you will find that by the light that you see, there is not enough matter to hold this galaxy together. So she figured out for us that there is a thing called dark matter through a technique called inference, which is critical in astrophysics. She figured out that there has to be a whole bunch of dark matter that actually helps hold this galaxy together through gravity. So we are, as a community, we have a high confidence that dark matter is a massive substance that holds galaxies and galaxy clusters together. But we can't see it. We have to infer that it exists until my colleagues in the laboratory can either smash particles together at high energies and make dark matter, or until they can detect it with new detectors that we're creating at Fermilab. So also through gravity, those galaxies like our own come together into large clusters. So here's a cluster where each of these yellow points, these yellow blobs, are galaxies. So they're held together by gravity amidst the expansion that I talked about originally. So just to give you a sense of what expansion means, imagine each of you are galaxies, and if the carpet here is space-time, in a universe, if you were galaxies in the universe and you were far enough apart so that gravity was weak enough on those scales, then there would be more carpet coming in between you and pushing you apart even if you weren't moving in the carpet. That's what the expansion of the universe is that's happening. So what we really have, as I said, is this tug of war between something trying to push us all apart through the expansion of space-time and then gravity trying to pull us together. So what does this look like? So I've told you about the past. One of the ways that we best understand our theories of the universe is to make simulations in some of these huge computers that Ollie was mentioning. So what if we did a simulation that had expansion of the universe and gravity in this competition? What would it look like in 50 billion years? So what you're seeing here are dark matter particles simulated. They're about the size of galaxies being pulled together into this large megagalaxy. And what you saw, I'm going to back up actually, do this again. You're going to see pieces go away and never come back, go away and never come back. So you're actually, what's happening in 50 billion years, there will be a megagalaxy like this here, and there will be another megagalaxy over there, another megagalaxy over there, and all these megagalaxies will be so far apart and moving so fast away from each other that they will never know that the other had existed. This is the effect of the other thing that we can't see in the universe that makes up most of the energy in the universe, called dark energy. So this is the quandary that we face. We will live in these island universes in 50 billion years when, in 10 to the something generations of us. And they'll have to figure out how to understand the universe after that. So that's what our universe looks like in the future. The thing that I want to express a little bit more about what this dark energy thing is. So the universe has been expanding since the Big Bang. And for a period, that expansion was constant. About 18 years ago, we found out that there's this stuff called dark energy that's pushing things apart faster and faster. This is accelerating this expansion. This is what makes it possible for those megagalaxies to never have seen each other. And it's like throwing an apple up in the air, and it's sort of sitting there for a second, then going further up. It's like, I don't know, if Michael Jordan had jumped from the free throw line, dunked, and then never came down. I don't know. So this is what the universe really looks like to me. We're just a small slice here. There's a whole bunch of dark matter that helps hold things together, and there's a whole much more dark energy that is pushing things apart. Ooh, how am I doing on time? 5. All right, we're good. So how do I spend my time and the taxpayer dollars to figure out more about this? And what does it mean to go to as the title of my talk said, what does it mean to go to the ends of the world to see the beginning and the end of the universe? So let's take a quick journey. If anybody here had trouble with the Hunger Games because of shaky cam, I'm going to show you a little time lapse here that goes from, Actually, the time lapse in a second. The journey that I'm taking is from Chicago to Austin. I'll have a layover there, and then I'll go down to Santiago, Chile, and then I'll go back up to a place called La Serena, Chile, an oceanfront town here. And when I get off that plane after about 22 hours of travel and amazing Adam Sandler movies, I get into this taxi, and for about another 2 hours, I'll try to remember the Spanish I learned in high school and college, and while falling asleep, and we'll traverse through the mountains and past many villages and communities to get to the telescope that I work at. So as you can see here, it's an amazing bit of scenery. These are amazing communities that we have the privilege to visit and interact with when we do our science from afar. So if you go up this mountain, after you do this about 10 times, you get used to it. So it's not going this fast because it's a time lapse, but the guy goes really fast up this mountain. You get used to it, usually by just letting yourself fall asleep. So it's cloudy here, but one of the reasons we go to such high altitudes is because the clouds are much thinner, and there's less to block the light as it comes to our telescope. So there's a telescope, we just passed it, and there's me hitting a button. And what's next? So this is the evenings. Here's another time lapse. You can see this is the dorm where we sleep, and they make us lots of meat and cake. No alcohol, though. That is strict because this is a mountain. You do not want to fall off it. You want to be just looking up. You don't want to hurt yourself. So you have a whole bunch of small telescopes here. Oh, that might be me coming up. I think it is. So you have a whole bunch of small telescopes here. You have the sun setting, and then we go to the nighttime. So what you're going to see now is the sky rotate about the South Pole, and you're going to see two dwarf galaxies turn amongst the sky. And this is the 8-story dome where we do our science. Right at the bottom here, this is about the size of a human. Right, it's hard to see in this movie, but right there, that's about the size of a human, right there. Again, size of a human is this gas tank. This whole thing, this is the Victor M. Blanco telescope. This whole thing weighs about 300 tons, 1/7 of the space shuttle, or a few brachiosauruses. And Fermilab built this camera. We did this over the course of 10 years. In this picture, light is coming in from here, bouncing off the mirror, and going into a whole bunch of electronics that holds about 600 million pixels of technology that can see billions of years into the past. At night, you see our telescope scanning the sky. As the moon comes in a bit, we avoid the moon, but it's there. So I want to point out here that we're no longer looking into these eyepieces like Hubble did 100 years ago. Right now, we're using computers and simulations to sort of we're teaching the computers where to look on the sky at a given time, because it has to scan so fast and has to scan so precisely. And this is one of the small images that we get. So DES gets about 1.5 terabytes a night. That's a terabyte, not a petabyte. Future telescopes, like another one that's going to go on this mountain called LSST, lsst.org, shameless plug, they're going to get about 1.5 petabytes a night. So I guess that you guys got 50 in a year? Yeah, that's right. Like 500 in a year. And this is what we get from that. So this is actually a picture from the Sloan Digital Sky Survey collecting hundreds and thousands and millions of galaxies where you can see the structure in the universe far, far away. Each of these pixels has many, many galaxies in it. So these are the kinds of patterns that this pattern was created by that tug of war that I talked about, and so we look at these patterns to then infer how much dark energy and dark matter is actually in the universe. So I'm almost out of time, so I'm just going to push a little bit through this. Thinking about big data. We live in a world where we can't all handle all the data that we see all the time. So what are we doing? We're making self-driving cars. We're having artificial intelligence discover new kinds of skin cancer that doctors might not have seen before. Or you're having a computer tell you how to use the rest of the stuff in your pantry to make a cake. I don't know if it will taste good. And our choices, the choices that we have to make, like what we're going to watch on television. Algorithms are helping us do this. So we have, maybe you've heard of paradox of choice, too much to think about, so we have machines help us do that. So what we're trying to do at Fermilab is turn this paradox of choice into an opportunity for discovery. What I mean by that is you have all these choices here. How do you figure out what the best one is? What if I could teach a machine to find the right kinds of galaxies that could teach me particular things about the universe? And that's, this apparently is some kind of artificial intelligence robot founded on Google, and that's your future, finding galaxies. Thank you.
Thank you, Brian. Brian also conducts guided trips to Chile if you want to accompany him next time, but it's a slightly long trip.
$5,000.
So our final speaker before we open it up for questions is Anna Grassolino. I first met her over a decade ago in Vancouver when she was stationed there to pursue her PhD in particle physics. What impressed me then and what still impresses me now is her passionate intelligence. These aren't words that people often combine, but Anna's the type of person you'd meet at that cocktail party and find eminently fascinating, charming, and mesmerizing, even though she was talking about magnetic flux pinning in a niobium-coated surface using measurement of RRR resistance. Anna is a scientist and deputy head of Fermilab's technical division. Her work focuses on the development of superconducting radio frequency, or SRF, accelerator technology. She's one of the lead scientists involved in the development and production for the new free electron laser at SLAC in California. Anna is the recipient of many awards, including the 2017 Presidential Early Career Award, which some believe would have her meet the president. We can decide later if that's an award. Anna holds a PhD in physics from the University of Pennsylvania and a Master's of Electronic Engineering from the University of Pisa in Italy. Anna, all yours.
Thank you, Tim. Thank you for the nice introduction. So I think my talk is going to be the less fascinating one. I'm the nuts and bolt person. I'm the person these physicists go to when they need to do the physics that they need. They come to me and they say, can you build me an accelerator that gets me to this energy? And you know, they come with all sorts of crazy requests. But I think it's really great because pushing the boundaries of human knowledge is really what drives us and gives us the motivation for pushing the boundaries of accelerator technology, which allows to make scientific discovery, but I try to convince you with this talk that it has also very important repercussions also in other fields. So with this talk, I tell you a little bit about what an accelerator is and what a particle accelerator is and how we try to make it better, what the current forefront technology is, and we are very proud at Fermilab of the fact that we are really the lead, among the lead laboratory worldwide pushing the boundaries of accelerator technology. So an accelerator is a device that uses electromagnetic forces to accelerate particles, and the main building blocks, the essentials are, so it's essentially what you see here. It's a very simple example, very familiar, but simple example of an accelerator. You need a particle source, so electrons, protons, or ions, depending on what you want to accelerate. You need vacuum, and then you need electric field for accelerating, and you need magnetic field for focusing and steering. So these are the main two things we work on. Electric fields for acceleration means accelerating cavities, and what I show here in this picture is really the forefront technology to imprint acceleration to a particle beam. So these cavities are made out of niobium. It's a superconductor, which means that if cooled down under a particular critical temperature, which is 9 Kelvin, so these cavities work at around 2 Kelvin, which is colder than outer space. At that temperatures, they lose all resistance to currents flowing through. So essentially, they become extremely efficient. So in about a meter structure, you can get 50 million volts, and they dissipate just as few light bulbs. So they're extremely efficient structure. They have among the highest quality factor in nature, of the order of 10 to the 11. So those are how we impart acceleration to particles and how we steer the beam. So if you want to keep them on a certain trajectory, we use magnets. And even for magnets, the key technologies right now is superconductivity again. So superconducting magnets is what has enabled LHC and what will be enabling future machines. So this is how they look like. And one key message that I want to pass is, how do we push the boundary of this accelerator technology? Actually, it's quite interesting how particle accelerators are really large installations. You see these kilometers and kilometers of either round or linear machines. But in reality, it's fascinating how the whole action is played into nanometers, in the nanostructure of the surface. So the tools that are essential to actually push this technology forwards are material science, understanding of the nanostructure. So a lot of what we do is we take these large-scale structures, we are creative on how we treat the surfaces of the structures, and then, which is a little bit like cooking, and it's a little bit empirical. But then, once we see how it performs, and we understand what we have changed, we then dissect, for example. We cut holes, and we extract small samples, and then we put them under microscopes. We put them under advanced tools like secondary mass spectrometry or transmission electron microscopy, all possible advanced surface analytical techniques to really understand what it is that this new surface treatment that I applied to this big structure has changed in terms of nanostructure. Modern accelerators, they are for scientific research. Early accelerators were motivated by nuclear physics. Today, particle accelerators, though, are essential tools of discovery for, yes, elemental particle physics, which is what you heard, but also nuclear physics, but also materials, biology, chemical science. I will say a few words about this. And also, I think it's important to emphasize that there are a lot of non-scientific applications. So accelerators have found broad and expanding uses in industry, energy, medicine, environment, and security. So all that we do in pushing the envelope of these technologies then immediately has applications for society, for medicine, which is extremely important. And that's part of what Charlie was saying earlier, that part of his job is actually taking these technologies that we develop and transfer them to industry. So discovery science and society application drive advances in accelerator and vice versa. So you can imagine accelerators as huge, powerful microscopes for studying the ultra-small or the ultra-fast. So this kind of tells you what timescales are accessible to us and what are the instruments that we use to see different size objects. So this is why we build this big particle accelerators, to really get to see in the extra small or in the extra fast. You heard about this, so I don't have to go through again. There are some amazing discoveries that have been made in particle physics with these big accelerators. It's about, so LHC is a prime example. It's about 27 kilometers. It's a proton and ion collider, 14 TeV. But the key enabling technology there is superconducting magnets. So you use both cavities, but when you have a circular accelerator, the magnet is actually more important because you have to keep particles in trajectory. When you have a linear accelerator, the cavity is more important because all that you want is essentially bring a very high energy on a linear trajectory. So this is where they are with 27 kilometers, 14 TeV. What's next for Europe is actually they're already dreaming of a machine that will go to 100 TeV. 100 TeV, how do we get there? So for current technology, for 14 TeV, the magnets are about operating at 8 Tesla. To get to 100 TeV and be in a reasonable radius, you have to go to either 16 or 20 Tesla. So 20 Tesla would be still 80 kilometers. So very, very large machine that would be under Switzerland and France. So to appreciate the importance of pushing the technology, this is from Enrico Fermi notes on what can we learn with energy accelerators. So the extrapolation was of Fermi to year 1994, that with 2 Tesla magnets, you would need a 8,000 kilometers radius machine to get to 3 TeV. So luckily then, superconducting magnets were invented, so we could go to 8 Tesla, so you didn't have to build something of the going around the Earth, but we could build the LHC, 27 kilometers, and see the Higgs boson. Or Fermilab with MBTI magnets, we could see the top quark. So again, this to appreciate the importance, how we go to the next, how we make the next step in seeing what's beyond the Higgs boson, in learning and going to these very high energies, we have to push the technology to 1620 Tesla. Are we there yet? No. Part of what we do at Fermilab is understanding how we can push these materials, and in particular, the material currently used in LHC is niobium titanium. Now we go to another material, which is niobium 13. Can we get to 16 Tesla? Can we get to 20 Tesla? Actually, here is a not so fascinating picture, but this is how they look like. This is a cross-section of a conductor. It's one of the small pieces, building blocks of a magnet. To push to 16 Tesla, you can make it with this material called niobium 13. To go to 20 Tesla, you cannot make it, and you actually have to go to high-temperature superconductors, which is also very fascinating field. So this is really the direction we are trying to go to get to higher energies. Another technology which is enabling for particle accelerators is, and actually I'm very familiar with, is superconducting RF. So those are these cavities I was talking about. So this is an animation. So you see it's a meter structure. You have electromagnetic fields inside. It's like a surfer that goes on the crest of a wave. So you have the beam going through, and you try to synchronize the beam with the electric field so that you always see positive acceleration. And again, in about a meter structure, you can get 50 million volts and dissipate very little. Now, what is so special about this technology? The older technology is you take a cavity like this, and it's made out of copper. However, copper cannot sustain being on for too long, because otherwise the walls will overheat and the structure will actually melt. So that's why you have to move to superconductors. And at these cryogenic temperatures, at this very high efficiency, you can allow the structure to be on all the time, which means you don't have to pulse the beam and have here one bunch comes, and then you wait, and then another bunch comes, and then you wait. But in reality, you can have bunch, which means you can have much higher intensity. So this is one direction where Fermilab is going. We need to have the highest intense beams for our neutrino program. And this technology allows that. It allows to have the most intense beam ever. This is a map that shows you how many actually of these accelerators that employs this technology are worldwide. It's really impressive. So this gives you a scale, and there are many more planned. Here's one example of why this technology was actually partially born. It's the International Linear Collider. It's currently proposed to be built in Japan. It would be about 40 kilometers of this superconducting structure. So think about a linear collider, 40 kilometers of these cavities, reaching about 1 TeV, where, so you would think it's much lower energy compared to what already CERN reaches. However, it would be an electron-positron machine, which would mean much cleaner events. And so that means that essentially you are able to, it's a more a precision machine. So you don't reach the highest energy, but you can reach the highest precision. So maybe like a higher resolution microscope, you can think of it this way. Other applications very interesting of these machines based on SRF technology are X-ray free electron lasers. What we can do with this machine. So first of all, there is one that has just been built and commissioned in Hamburg. It's the European XFEL. It's not very high energy. It's not very large installations. They are sources of light, which means they allow you to study, for example, proteins. You can do molecular movies. One that we are building here in the United States, it's called LCLS2. We are building it at Stanford, at SLAC. And it will have, so you can see here in this little movie, it will allow you to see chemical reaction as they happen, for example. And it's really unprecedented because with this technology, we can get very high time resolution, so femtoseconds. Again, this technology is also enabling for our neutrino physics program here. So we are in the process of building one accelerator based on this superconducting technology at Fermilab. It's called PIP2. He will accelerate protons. And then from there, we will eventually produce neutrinos. But again, the key here is that we can have very high intensity beams. And so we will have the most intense neutrino beam in the world, and we will be leader in neutrino physics. How are the performance of this structure pushed? I did mention briefly that you see there, you have these big structures, and they are made out of like 3 millimeters thick niobium, but in reality, if you zoom in, you can see that it's the very, very inner surface of the structure that matters, so only nanometers, so about 20 nanometers from the surface. And so the final treatment of this, and here is a picture that gives you, this is the inside view of the structure. So how you treat this surface, which is a combination of chemistry, high temperature treatments in high vacuum ovens, cleanliness, everything, all these structures are in semiconductor grade clean rooms, so only class 10 clean rooms, which means there is only 10 particles in a cubic foot. So everything is extremely important to allow these structures to perform at this 50 million volts per meter with these very, very high quality factors of the order of 10 to the 11. And a lot of the research that we do at Fermilab is really pushing the understanding of superconductivity under this radio frequency field and the nanostructure. So accelerator impacts our lives in fundamental ways: discovery of scientific knowledge, particle and nuclear physics, material science, biology, chemistry, and there is a very broad range of application. Accelerator science is a tremendously exciting era as we envision new breakthroughs powered by new concepts and technology. We have a fantastic team, I want to say that, of engineers that work harmoniously with scientists, a lot of young students, really pushing together from the engineering front, but also the scientific front.
Thank you, Anna. So we're now going to accelerate our conversation. So hopefully this mic is picking me up. So some of you may have noticed that our screen is slightly shifted. I'll just blame that on budget cuts. We can only afford 95% of a screen. Now, I do want to, one of the reasons we came out tonight was to have a chance to actually talk with you and hear some of your questions rather than just our views of what we think is important. So perhaps if you want to start formulating a question, I'll give my colleagues here a softball, and then maybe we'll turn to the audience. So, you know, we've heard a lot about the progress of science, and then you can see there's computing, there's accelerators, there's materials, there's astrophysics, there's the expansion of the universe, and what happens in 50 billion years. So let me ask you just, you know, how, at a place like Fermilab, how do you stay abreast of what's happening? How do you find out what just happened? How do you find out what's going to happen next?
Twitter.
Twitter.
Nigel's Twitter.
No, but this is actually a very good topic. Particle physics was essentially the first ones who really used the World Wide Web. The World Wide Web is based on network technology that was developed by DARPA, but the actual making it useful, HTML, having web pages, that was first done at CERN, and then very quickly was moved over to Fermilab, and we were the first ones who actually had a web server. So fnal.gov is one of the oldest web servers here in the US. And this is how we actually stay informed. It is, you really have to imagine that there are thousands of papers coming out, and they are all online. It's not anymore that you have to go to the library and are relying on that somebody has bought the journal of the paper. So you really have access to everything instantly. It is a challenge to keep informed, and we're reading a lot of papers, but it's essentially heaven for a scientist because we have everything to our disposal right now to stay informed.
It's also in-person conversations with colleagues. Walking to my car, or we don't have water coolers, we're not allowed to have them. So, getting coffee or something at the lab, ideas just spark, and we'll share with each other, oh, that'll work, well, but that won't work, oh yeah, it will, because I figured out this thing just a minute ago. So the way that we come up with new ideas and the way that we hear about what our colleagues are doing is also through these in-person interactions. So conferences, workshops, just going to visit colleagues are super important. So you can see some of this happen if you ever go to, say, a AAAS conference, I forget what that acronym is, but American Physical Society, an APS conference, or American Astronomical Society. Sometimes parts of these are open to the public, and you can be a part of some of those conversations sometimes.
By the way, the coffee on the CMS floor in Wilson Hall is the best coffee because we brought it over from Switzerland. So everyone is coming to our floor and we get the best information.
Coffee is always a gathering point. When I came to Fermilab first as a summer student, and in technical division there was the best Italian coffee machine, and it was the gathering point where everybody was exchanging ideas. No, but jokes apart, we also have weekly colloquium where we invite speakers from outside, and this is a wonderful venue for learning a lot. And seminars, accelerator seminars, particle physics seminars. So we have a lot of weekly meetings where we foster exchange of ideas.
Thank you, guys. So maybe turn it over to the audience. So questions? You guys want to choose, or should I point? Got one back here. I feel rude. That guy.
Thank you very much for the interesting discussions here. Regarding accelerator science and moving forward, especially the high energy, like a follow-on to CERN, these are very still big machines, very expensive. Do you see hitting into like you just can't create them anymore due to the cost? I mean, you're asking society to dump a lot of money into some, nice, very fancy toys. It's not that I'm against it, but we're talking serious dollars at this point.
Yeah, what is the question though? It is an observation that they are expensive, but...
I think there's two parts I heard to the question. One is, are we on a path where it'll be not too big to fail, but too big to build? And the second is, how do we deal with that conversation about it seems like the ever-increasing price tag for discovery?
Mm-hmm. So, my job is exactly that, to actually bring the cost down of these machines. Now, can you bring them down a factor of 10? Possibly you could. There are some of the ideas that I showed here, probably they could bring down a factor of 2. Factor 10 or more will require more innovative ideas, like, for example, plasma acceleration, accelerator on a chip. There is a lot of accelerator research in the US that it's also towards really not going to megavolts per meter, but gigavolts per meter. So that's also another avenue. In general, if you want to put a price tag, I guess we could, a machine like the International Linear Collider, the one that Japan proposes to host, has a price tag for 1 TeV, even let's say for 500 GeV as a start, which would be a machine that will study in detail the Higgs boson. So now that we know where it is, what are really the properties, so that we can understand better how to move forward from there, has a price tag of about maybe 6 billions. So it's expensive, but in reality, I don't know, it depends what you compare to it. You get 20 years of physics, you get training of young people. I think you get a lot for the buck. So it's not, there is a lot that comes other than the discovery of new particles. There's a lot that comes with it.
You also have to see that we're living in an international environment. So we're bringing the world together through science. For example, the LHC has a price tag of $15 billion. It took 10 years to build it. It will produce physics for 25 years. It will produce thousands of PhD theses. We're currently passing the 500th paper of CMS alone. So multiply that by 4. That's current, and we're going to run for another 15 years. So the amount of scientific knowledge you will gain from these kind of investments is enormous. And you have to then divide it by 35 years.
And then also, of course, the spin-off of the technology, right? For example, development of superconducting magnets has positive impact. For example, clearly the prime example is NMR, right? MRI. So, I mean, again, I think there is a lot that comes with
Brian? There are papers that are coming out, but what comes from these papers? Like Anna just said, technology that saves lives. So it might look like we're playing around somewhere, but we are playing. There is play to it. That's part of what discovery is. But the results are real. And I think when you've heard these numbers that are 6 billion or 15 billion over the course of many years, how much does an F-35 cost? So I think it is critical to ask these questions. How much are we spending? Are we being as efficient as we can? But when we ask those questions, we should also approach the answers in context.
I think it just, not that we want to make it all about money, but I think it's an interesting anecdote. If you look, the first Boeing 777 cost $32 billion. The 10th one cost less than $1 billion. You're always making the first one as an extraordinarily expensive. And that's one of the challenges that we have in discovery science, is you're building the first of a kind and you're fronting all of that effort up front. But then it feeds into other activities. But as Brian said, just to echo, putting it in context, these are critical questions. It's important, particularly in this day and age. Next thought. Maybe you guys can see better than I can, so I think Sasha.
I think she had her hand up pretty early on, too.
In the first row.
Oh, first row here, okay. I've been outvoted. First row after the lady in red.
Okay, thank you. Well, sorry to continue the money trail, but I do think it's important, and I wonder with all this conversation that's going on about budgets and DOE and everything, are you going to get what you need this year or anywhere close to what you have been getting?
Maybe this is a question for Tim.
It's a good question. If you happen to know what we will get, I'll personally bring you $1 billion. But I think democracy has many pluses and minuses. We're experiencing the checks and balances right now. So right now, I would say at a place like Fermilab, we think in the end we'll end up roughly where we need to be to continue doing what we came here to do. And that's a combination of parts of the executive branch. It's conversations with Congress, which does have the final word on some of these key issues. But then we wander into issues like immigration policy and how can we actually bring the world together in the face of some of these other conversations. So it's a challenge right now to predict the future. But our view is we're still doing what we came here to do, and it's still valued by a lot of people. So maybe we'll go up here front, and then I saw this hand here, and then we'll go back.
Niobium is a rare earth element. Where does it come from, and how reliable is the supply?
Thank you. Good question. It comes mostly from Brazil, but there are several vendors worldwide that we use, and I think it's not as cheap as copper, obviously, but it's not an issue. It's reliable. Yeah.
Let's go here. I guess I am choosing this.
Thank you all for your really informative and wonderful presentations. I've got 100 questions scrawled over this little Costco junk mail here. I'll just do one, though. It's probably for Brian, but anyone can jump in. I think on your sort of classic picture of the expansion of the universe, there's that the Big Bang and then the big period of the Dark Ages where there's no matter that seems to reflect light, and then there's the explosion 400 million years later, I guess, there's this explosion of stars. Is that just an explosion of matter that reflects light? It just says 400 million years, there's an explosion of stars. Or is it also an explosion of the dark matter and dark energy that you work on, and then how do you know that?
Right. That's a good question. I will unpack as much as I can. Around a few hundred million years after the Big Bang, what has happened is most of the matter in the universe that we can see that interacts with light is just hydrogen. It's mostly hydrogen. And after there's been so much time in the expansion, there's been a cooling. So hydrogen is being now, it's cold hydrogen, and is being pulled together by gravity. And that gravity pushes the hydrogen into what become cores of stars that eventually result in fusion and emit light. We don't have any evidence that dark matter does the same thing. So as far as we know, it's only what we call baryons, from Greek bary meaning pressure because they feel pressure. These things that emit light or interact with light, these baryons, are the only things that we know that come together and eventually fuse. There are theories out there that there may have been, some of the earliest stars may have been dark matter stars, but none of that has been either observed or really, I think, connected rigorously or precisely to some early observations. And dark energy, as far as we know, doesn't clump at all. It's a very, very strange substance that, if I wanted to be super flippant, I would just say all of what we know is basically I could fit on my hand in 10-point font, but it's not that bad. We know a lot more than that, but sometimes it feels like we know that little. So baryons clump, form stars. Dark matter can clump together. People look for signatures, say gamma rays coming off them, but we don't know if they make stars, and dark energy doesn't clump as far as we know. So, right, so thank you for bringing that back up, the rest of your question. We don't know when or from what process dark energy may have been created. The current basic theory that still fits all of our models, or fits all of our data, is that dark energy has always existed, but that 4 billion years ago, only coincidentally when planet Earth came into existence, did the expansion reduce the impact of the effect of dark matter and other things such that we could essentially infer that dark energy existed. So dark energy became a dominant force in the universe 4 billion years ago. But we think that it existed before that. And dark matter, there are other similar theories, but we don't know what kind of particle dark matter is. We just know that it feels gravity. So we don't really yet know when or where it was, but when it was born.
Thanks. You've been wonderful. We were just talking about funding, and I was wondering, because you're creating all of this knowledge, does Fermilab have access to making money off of patents and licensing?
Yeah, maybe I'll start and then we can talk about a few examples. But yes, I mean, the US government, we're working with taxpayer dollars, and there are certain pieces of the law that dictate that the people that make the discoveries can patent that and turn it into a business. I think part of the first 50 years and maybe the next 50 years at Fermilab is the initial model was just what Ali described. The World Wide Web was, this is a tool for me to talk better to my other science and engineering friends. Why would we want to patent that and turn it into a private business? I'm interested in just getting more sharing going on. Same thing with the magnets that Anna described, is these were magnets developed for accelerators. We worked with GE to develop the technology and said, GE, do you do what you want to do with the technology now that you know how to make a lot of these really fast? And GE said, I can revolutionize medical imaging with MRI. The new model is, well, maybe some of these things we do want to keep our eyes on and stay involved in. So we may be exercising a bit more of that right built into the legal structure. I don't know if anyone else wants to comment on that.
I made a discovery that cut the cost of the accelerator we're building at SLAC by probably 100 million. I didn't patent it because I felt that, you know, if you really want things to take off and move, and if you put a patent, it may limit the speed at which, right? So that's my experience.
As we build our software packages that will permit new advances in AI to be applied to our lives, I don't know how I would handle that situation exactly, but I think it's important to ask the question, if taxpayers are paying some of my salary, should there be a way to help fund our activities based on those discoveries? And I think it depends. It's going to have to be on a case-by-case basis.
And we are collaborating with industry a lot on large scale. in my field, in the supporting computing world, I mean, you have the big players, Google, Amazon, and all that, and we are really working together, and in the end, we will all benefit, and we will have the opportunity to essentially get very good prices from them to lower our base cost to do our science. So I think there's a lot of balance in there, and we are very aware of our potential creation potential that we have, and we have lots of good people that work with us to really make sure that we can benefit from these things in the long term.
Thank you. I would. We've been talking about future plans and developments. I'd like you to be more specific. Do some bragging here. I mean, here's Fermilab, 50 years. Okay, it's been here for 50 years. CERN has been around for what, 10 years? And there's a lot of talk of super telescopes that are being planned and built, and the James Webb Orbital Telescope, and lots of plans from NASA for all sorts of more spacecraft and a long heritage that they've been bragging about all the amazing things they've been doing. Well, where are all these hundreds of billions of dollars going exactly? What's the next CERN? What are the next 5 or 6 big projects we've got coming up? Where are they going to be? What are they going to do? How much are they going to cost? I'd like some details.
Maybe, Al, you can put CERN in context.
All right, good. So CERN's age is actually 60. So CERN was founded a little bit earlier than Fermilab, actually. And the next step for this collider-based research is, first of all, the International Linear Collider that Anna mentioned, price tag $6 billion. If that is going to be realized, we can pin down the properties of the Higgs boson, and we can really understand it and really solve the mystery of why it fits so well with the theory. I mean, this is really disconcerting for a physicist. If there's a theory and it fits so well with everything we can measure, something must be wrong. So that's what we're trying to figure out with the International Linear Collider, because it's a very clean machine. The next thing is the next stage of the Large Hadron Collider, because you have to see a proton-proton collider is very messy. It's 2 big particles, and it's actually a mesh of particles that you slam into each other, and there's a lot going on. And we're going to increase the energy for the so-called high luminosity LHC that will start in 2026 at the same time scale as DUNE, as the new neutrino experiment. We will actually produce more data than LSST. Thank you very much. And at that point, we hope to actually play a role in answering what dark matter is. Because with a lot of data, we think we can find the needle in the haystack that points to what dark matter actually is.
Do you want to talk about LSST for a moment? Or?
Sure, I can talk about LSST and its predecessors. So to be specific, Fermilab has been in the astro game. If we're talking about optical telescopes that see from, say, red to blue wavelengths, they've been in the game since the Sloan Digital Sky Survey, so sdss.org. If you go to that website, I don't know if they'll have that picture, but the picture that I showed that had the cosmic web, where there's a whole bunch of galaxies in 1 pixel, that picture, we were critical in developing the software and the data management and a lot of the science that came out of that data for understanding that dark energy exists now, for measuring how much dark matter there is cosmically. So that took place in the early to mid-2000s, actually we'll say 90s and early 2000s. And then Dark Energy Survey came along. This is the next telescope that sees farther and deeper and sees, instead of the size of the sky and the number of galaxies you saw there in SDSS, we're going to see 500 million galaxies in Dark Energy Survey. So if you go to darkenergysurvey.org, and actually I helped build this website, so there's bragging. We just released our first year results, which are just the first set of, this is 1 year of data out of 5. So we're going to have 5 more years of data to learn about what dark energy is. But we just came out and we proved, essentially, that new, difficult techniques to use on this kind of data are possible. What we did to measure it with precision has not been done before. And the Large Synoptic Survey Telescope is an even bigger thing that Fermilab is a part of, and so is Stanford, that's going to see billions of galaxies and essentially take a picture of the entire southern half of the sky every 4 days. So with that data, we're making a movie of the universe over the course of 10 years. We're going to be able to see planets. We're going to see supernovae go off. We're going to see lots of things that are going to tell us about potentially life on other planets, that tell us about how fast the universe is really expanding. And one thing I just want to be clear about, this basic research, it's something that as a society we should dig deep and try to understand why we do it. So we talk about applications, we talk about spin-offs, all of that is critical. Like we need to be making those technology transfers, but there's another deep question. Why do we ask these questions about the universe and about where we come from? And I think we should spend some time asking ourselves that, at least as much as we're asking ourselves what the spin-offs are.
I will give one plug just for the opening movie, since I didn't make the movie. But you know, the flagship initiative for Fermilab, and in fact U.S. particle physics, is this next generation neutrino experiment. It'll be the biggest, baddest neutrino experiment in the history of time, and we think, I'll call it, we'll do prize-winning science. We have 1,000 scientists already signed up from around the world that want to come to the Chicago suburbs and the Black Hills of South Dakota to join this project, and we'll start actually the scientific experiment in about 10 years. So that's bringing together 30 different countries that want to come to the United States to do some amazing science. And that's in the world of neutrinos, which is sort of one of the counterparts to the Higgs boson. Something we know is there, but we don't understand it very well. Next.
I think my question for Brian, you touched a little bit about artificial intelligence. Are you doing research on that, or are you just using that? Because there's lots of artificial intelligence industry now, the research, lots of big companies spend lots of money on that, but it's also talking about the danger of the artificial intelligence. Maybe they're going to start the Third World War. What do you think about that? What's the future of the artificial intelligence?
So this is a really good question. This set of questions is very good. These are questions that we should be asking, because more than we know, algorithms dictate is maybe a strong word, but algorithms guide our lives substantially. And I think it's going to increase substantially. The ideas about war and robot overlords, those are things that there's a piece of it that we should take away, which is our humanity, is how we treat each other, is that keeping up with the technology that we use? Because ultimately it's us who decide how and when to apply these algorithms. So I'm concerned about jobs. What are jobs going to look like in 10 or 30 years? If you listen to Andrew Ng, who is one of the, he's a former Stanford professor, he started Coursera, he's one of the founders of this, what's called the third wave of artificial intelligence. He would say that a radiologist may not have the same job that looks anything like it in 10 years. Because the technologies that we're developing, what they can do is take complex images and give us sort of human readable answers from these images. They can help us find these patterns in complex data. So I think it's a critical question to ask. What does it mean to have so much of this technology running around in our lives, and how are we going to deal with it as a society? Fermilab just started actually recently what we're calling the Machine Intelligence Group. So another associate scientist and I, Gabriel Perdue, we're the sort of co-leads of this group, and our aims are dual. One, to apply wherever appropriate artificial intelligence software and algorithms to physics data, and two, advance artificial intelligence in a way that can, again, serve physics problems. So we're trying to do both, and we're just getting started, but we think with increases in technology like GPUs and the algorithms that we're going to help invent, that we'll be able to understand better this technology and help usher it into society in a way that's better for us all.
I would like to comment from my point of view, from a scientist's point of view, is if you look at Netflix, if it suggests a movie for you or a couple of movies, it doesn't matter if it gets it wrong 1 in 10 times. You say, okay, that's a bad movie, I'm not really interested in. But if we want to responsibly use artificial intelligence and these techniques in our science, we have to dig a lot deeper into how they do it, what they do, and how we can apply it. And I think this is really the way of using technology in a responsible way and helping society to see it as well in a very detailed and scientific way what these things can do.
They're in criminal justice systems in the United States, algorithms are used to help figure out who maybe should be let out of prison or maybe who should be profiled. There are known flaws in these algorithms and their usage in criminal justice system. There is clear data that they target people of color more than they target whites. This is one of the clear examples this is one of the reasons that I've decided to pursue artificial intelligence along with astrophysics, because I feel like I need to understand this thing better if it is going to play such a large part of our lives.
Next easy question.
Hi. I'm a big Harry Potter fan, so just wanted to say that. So there was episode, and it was called The Deathly Hallows Part 1. And I'm big on, I love technology, don't get me wrong, and I was listening, and I see how technology is like where I look up one little thing and I get like 120 trillion results, that I have to go through, and I'd be like, wow, okay, I gotta go through all this to find what I want. But it's good to have, all those options and stuff like that. But my question is, out of all the information and stuff we see in the sky, I believe in stars. So I believe that information can be held in a star and we can draw it down. I don't know if that's true, but we can draw it down and be able to get that information, be able to see, what we can do in the future, or maybe even store it, like the sky can be a storage space, I don't know. But are we giving, in all this research, when will we give back to be able to enhance ourselves more? Make us instead of an Iron Man, maybe a Superman. Where we be able to zap some energy out of a stick or something. When would that happen? When we give back to ourselves? Because one thing I want to depreciate age. Why are we still thinking about age? 34, 36, 37. We'd be like, oh, when we get 60, we get old. When we say old, so you think of death. And I'm like, whereas death is blackness. So why are we going back into blackness? Why are we not going into the light?
Believe it or not, those are some of the things that I think about. What does it mean to take the technology and improve our personal lives? And so I think if you look at algorithms, that's happening for better or for worse all around us. You mentioned more machines that affect our longevity. If you want to live for a couple hundred years, more power to you. I'm not sure. Maybe I do. I don't know. I like mortality. But I think the trajectory that we often see in science for how it guides us toward some of the science fiction future that we read about is slower than we would like. I know it is for my dad. He's been dreaming of flying cars for 20 or 30 years, and he keeps asking me why I haven't made him one yet. And I'm like, sorry, that's not how science works. But I think that there's that speed that we get to that futuristic world that we're hoping for is, on one hand, it's slower than we want, but I also like that futuristic world is kind of always sitting out there, because it reminds me of what I'm reaching for. It reminds me of the hope that I have for making change in the world. So I don't, sorry that doesn't buy you an Iron Man suit, but that's how I feel about it.
But I would like to come from a little bit of different perspective, because we're doing a lot with doing this large-scale science, with developing these huge detectors that can detect the smallest particles. We are advancing a lot of how you live in your daily life. At Fermilab, we are one of the ones who pioneered new cancer treatments by using neutron beams, and also even proton beams, which is really new. And it is very successful. It's that successful, actually, that we had to close our facilities because we're not allowed to compete with hospitals who have accelerators now to do these kind of therapies. And they all are based on the technologies that we need for our science. So you can see immediately how we better your daily life with what we do.
That's true. So a lot of these accelerators, as I partially showed in my talk, have application in medicine, like he's saying. There's cyclotrons producing isotopes for medical applications. There is actually a lot of application for society, for example, for water treatment, for asphalt, for treating, I think, bacteria from vegetables. There's really a lot of most disparate application for accelerators. In general, even the machine that we're building at SLAC, these sources of light, you really study, you look how chemical reactions happen, you look at how proteins unfold. I mean, a lot of these things are really key to make progress even in the medical field. So I think it's pretty clear that there is a very large return for society.
But we cannot really tell you what's coming.
I mean, I think what the challenge there is miniaturization, portability. Can we put one of these accelerators rather than building it in 1 kilometer? Can we build it on a tabletop, or at least in I don't know, 20 meters, so that it can be in the basement of every university, of every hospital? And this is really very close to the research that we are doing. By pushing towards new material that can be more efficient, we can make these objects much more compact, rather than having big cryogenic systems needed to cool them down. If you go to higher temperature superconductors, you can cool them down just dumping some helium on it, or even maybe nitrogen one day. And really, you can make it portable and more accessible. One thing that may be important to say is that, for example, another interesting spin-off of what this technology development that we're doing, these superconducting cavities can also be used actually as building blocks for quantum computers. So that's one new direction that we are taking at Fermilab, is research in quantum computing. So there is a very large effort worldwide. Quantum computing is the forefront, the future, that will allow to have much higher computing capability. And so there are many potential different technologies, one of which is called 3D architecture based on superconducting resonators, which is exactly what I showed. So if we can make these cavities have very high Qs, so what you need in quantum computing is actually having a photon, for example, that goes either in 1 or 0 state. So, the 3D architecture based on superconducting cavities would be a cavity with the Josephson junction inside, which is a qubit, and then this photon bounces back and forth. And this superposition of states between 1 and 0, so photon in the cavity or in the junction, is your essential quantum computation. So now the higher the quality factor of this cavity, the longer the computational time. And that's really the how you push the boundary of this technology. So we are now in the game among the leaders in this, potential leaders in this technology, because we have this unique expertise in making cavities with very high quality factor. So I think this is another example how technology that you develop for something like physics, particle accelerators, spins off towards something completely different, which is quantum computing, but they will have an important return for society as well.
Thank you.
Hi, I'm not sure whether this is for Brian or someone else, but you sort of
hinted at new physics, and that, for example, we don't know what gravity is yet. We haven't identified what gravitons are. Can you give us an idea of when you think that that might happen? I know it's hard to predict, but what new physics is around the corner? I think, dark matter is another possibility of identifying that. That would indicate new physics.
Okay, so I can give you a time range by telling you that it took us almost 50 years to really find the Higgs boson. And the Higgs boson, compared to dark matter, was really easy to find. So it all depends on how well we can look at nature and how well we can really look at different pieces of nature and say, okay, dark matter really cannot be here. And as successful as we are in this, then we can develop a program targeted towards where we really think that dark matter might be. It might be also that is completely different than what we think it is. And this would be actually much more exciting than finding, okay, dark matter is here. But I can really not tell you if it's now 20 years or 50 years or 100 years. Just remember, the electron was discovered 150 years ago. Nowadays, it governs our daily life. You cannot exist without the electron anymore. And let's see what the Higgs boson is going to do and what else would come afterwards.
So when Ollie was talking, when he was talking about the four forces, and he said, gravity, we don't understand that as much as we do the others. So on cosmological scales, we really, we get gravity. We're buds. On small scales, it doesn't fit with the way that we model or theorize the other forces of nature. So that's one of the critical problems we have with our theories of nature. But maybe one way to think about this is Einstein gave us a new theory of gravity at the turn of the 20th century, and what we're doing now, how we're trying to understand dark energy is in the context of that theory. So what we have to do is measure everything we can about dark energy, about the universe, to infer things about dark energy. We also have to test Einstein's theory. So what we're doing with these galaxy surveys, what we're doing with these other astronomical experiments, is saying, was Einstein right? How wrong was Einstein? And these are all important questions to ask because we have to consistently check what our theories are saying. So I also don't know how long it'll take us to really figure out what dark energy is or how it will ultimately exactly affect the universe. But I can say that we discovered dark energy in 1999. So it's been less than 20 years, and we're still trying to characterize, we're still trying to understand what it does to the universe, much less know what kind of particle it is. But if anybody wants to make a wager, on something, that's not beyond me.
Something big's going to happen next year.
Is Fermilab doing any work with antiparticles or antimatter, or do you have plans to?
So first of all, the Tevatron, that was the highest energy machine up to the LHC turned on, was a anti-proton machine. So we have a long tradition of handling antiparticles. But to reach really high energies right now, you cannot produce as many antiprotons as you want to accelerate them and collide them. That's why the Large Hadron Collider is a proton-proton machine. There are the International Linear Collider will have electron-positron, so electron and the antiparticle to the electron collide, which will give you the cleanest interaction and will pinpoint all the properties of the Higgs. And at CERN, there's an antiproton trapping experiment, which is really, really hard to do, because right now, if we keep antimatter moving and away from any other matter, we can really handle it. But as soon as it touches matter, of course, E equal mc squared, that's its energy. So there's an antiproton trapping experiment. And yeah, antiparticles are what we're doing. And by the way, Dune will have a lot to say about antiparticles, because I don't know if you wondered, but the Big Bang, E equal mc squared, where's all the antimatter, right? It's not there. And Dune could shed light with something called CP violation, in that nature is actually treating matter and antimatter differently. And that would explain it. So, a good question.
Hi. So I did a little bit of research on Fermilab. I'm a science teacher myself, so I'm 100% pro-science education.
Steve.
Hey, how's it going, Brian? So my question is, Fermilab was started under a very similar defunding of science nationally. If it wasn't space race, we weren't spending money on it. And the only way that Fermilab got to happen was through Robert Wilson's frugality of science, like taking everything. People were working in rooms with dirt floors, like leaking ceilings, and that's the way that we got Fermilab to be. I know that the world values scientific research, right? But it seems like there's a possibility that America might not value scientific research. If we need to shift back to Robert Wilson's frugality of scientific discovery, will science, especially at Fermilab or in America in general, survive? If so, how? Or is it just the smart people are going to go to places where the money is actually being put to good use?
I'll just say I got this jacket at Goodwill, so.
This was handed down to me by my professor. So it's all about your personal, how you feel personally about it. And let's not kid ourselves. If we would go to industry, we would earn a lot more with what we can do and what we bring to every project. But that's not why I'm in science. I mean, I'm in there for the science. I get up every morning for the science, and I work till late in the night for the science. So I think that I would be personally invested to find a way to continue doing science.
Just to add, I think it's an interesting conundrum you point to, is, how do we know when there's enough, and is it going down? So if you think about it, Fermilab runs on $400 million a year. That's actually a lot of money, a 10% budget cut. Okay, now you have $360 million a year to do science. So is that the end of the world, or is it, as you say, does it mean, okay, we've got to focus and maybe adjust what we're working on and maybe find some other partners? So that's one of the challenges here, is that the science is now global. So it's not one country that's dictating how the world pursues science. We do worry that smart people can go anywhere these days. If the United States wants to be a culture that values discovery and attracts some percentage of people to set up shop and live here, we're going to have to be attractive in some regard. And it's not just about the suburbs, which will bring everyone to the United States. We worry about this a lot, about the value. How does the public value science, and what do they look for in it?
I think a lot of people already left. I mean, most of the people that I was in grad school with, they were actually American, and they live in Europe. Paradoxically, I'm Italian and I live here in America. The reason I'm here is because Fermilab is leader in accelerator technology, but many people were particle physicists that didn't want to be here because the action was there. So I think a lot of people we already lost. We try to now regain by being leaders in neutrino physics, right? But so it's not about frugality. It's my people who come here from all over the world to work on superconducting RF research. They come because we are the leading center. They come here because we lead the research. They don't care if we do it. Certainly, you're welcome to come and see. It's very frugal. We don't have leather chairs. But yeah, people will go where the cutting edge research is, at least the best people. So if we want to retain talent, the real talent, we have to do cutting edge research.
I think Americans do value science. But we're diverse. America's diverse, so it doesn't mean that every single person values it the same. If you use a cell phone, you value science. If you drive a car, you value science. I think that it's up to us to work with our fellow citizens to share how much we appreciate science, so that those kinds of differences change a little bit, so that if we can communicate, not just us up here, but all of us we're here for a reason. We have some appreciation or some skepticism or both, but I think it's up to us to talk to our neighbors and have, if necessary, difficult conversations about why science is important and how it deeply affects our lives.
I'm assuming we're here till 10 p.m., so someone should indicate when we hit the
Hi. So I actually have a question along these lines that you were talking about. So Fermilab has had wonderful 50 years and hopefully 50 more. And you guys are going to be the leaders of neutrinos, wonderful. But is there any initiative, knowing the political climate and basically that 1 in 4 are scientifically literate, for Fermilab to use their clout, so to say, to expand accessibility to science to people who might be in that 3/4 range, where they're not either comfortable with science, don't like science, or don't understand science? So is that something Fermilab is doing? Or I assume you all identify as scientists, like that you in the scientific community would want to push forward as well.
Yeah, maybe I'll say something, and then I think each person here should add. Fermilab is firmly committed to sharing the story of discovery and innovation. So there's about 2,000 people that work at Fermilab, and we work with about another 4,000 to 5,000 people directly around the world. But every year, we're engaged in touching the lives of about 100,000 other people to talk about science and how it matters to them and to learn what matters to them. So that's just gives you a sense that we are committed to engaging more than just our bubble. But we're also thinking about what would it look like to double that? Is that the right number? Should it be half that? Should it be double that? One of the reasons we're each here is because we're interested in this conversation. But maybe, Ali, you want to start, right. Then Brian.
So personally, I try to, of course, I work a lot on my science and all that to enable it, but I always try to put some time apart to either give talks at Fermilab. We have this Ask a Scientist thing going on, that almost every Sunday there's a talk by a scientist, and then there are other scientists to talk to and to ask questions. We have programs at Fermilab where some of us go into high schools and talk to classes, or have experiments that high school kids can do and come to us. We have one of my colleagues just started a Girl Scout badge, which then Girl Scouts come to Fermilab, get their badge, and learn about science, which is really, really important. And these kind of small steps we're trying to take. And I personally feel very good about it, because I can go out, I can talk to people, and I learn also how to explain things that are admittedly rather complex in a way that engages people and interests people.
I really appreciate your question, because part of the reason that science is important to me is because I think that it is fundamentally about justice, actually. The more accessibility we have to science and to critical thinking that enables science, the more that we can make difficult decisions together, if we learn to communicate with each other, the more that we can handle nuanced situations for ourselves and for our society. So increasing accessibility for underrepresented minorities, for communities of color, for rural communities, for everyone who does not have access, that is for me a daily and moral imperative, because I want us all to be on the same page with these issues as much as we can. So this is a substantial fraction of how I spend my time reaching out to communities or bringing communities in and just being with them as a person who also happens to have trained for over 10 years to do science professionally. And I think it's important that we do what is the bit of the hard work, which is like bringing down this wall, this curtain that says that like we're any more special or any more useful than vocational work. I think that is a key thing that I think about very often. This idea of the ivory tower, and I think that does not help the dissemination or the communication of science. So I trained to do this. People here have trained to be experts in things. They spent their lives doing what they care about or what they need to do, and I see us as partners in that endeavor.
And we have a lot of summer programs, for example, where we reach out to actually different. There is American, there is one for Italians. So we pay a lot of attention to minorities, to diversity. So there's a lot of very nice internship programs. So we try to reach out a lot.
Okay, I think we're at the time where we'll take one more winning question. I see someone patient in the back with a hand raised high. So sorry, folks. I think there's a chance to mingle afterwards. So you can still.
Thank you all for your trenchant observations tonight. I think I speak for many in the audience in saying it was a very informative evening. Perhaps in some way my comments as the last questioner crystallized a lot of the issues. It strikes me that a lot of the discussion tonight, rather than focusing on the hard science, was really about the exigencies of funding the sciences, and justifiably so. And so much of the discussion inexorably seem to boil down to our broken political system, the frugality of the government, perhaps particularly this administration. I thought perhaps it was a little gratuitous to make caustic remarks about the president. I would like to think this was one forum where we could disassociate ourselves from any disparaging comments about particular politicians. But my broader point is, and I think the last gentleman touched on it to some degree in his very eloquent comments, isn't this really more, as it is partly a question of politics and economics, isn't it also a question really of first principles? And by that I mean cultural considerations, the cultural ethos of our society. Aren't we moving away from a society, and it really can be traced back to our educational system, where the notion of critical thinking is being disparaged or perhaps debased. And core curriculums, which were sine qua non in the American educational system, are being diluted by a lot of, if you will, artsy-fartsy liberal arts. Not that there's not a utility to that in societies, but as we become more and more scientifically and technologically oriented, there really is a premium more than ever before placed on the immersion in the sciences and in the technologies, and that begins at a very young age. And it just seems to me these are not just political and economic considerations, but also cultural considerations. And perhaps that's gotten short shrift tonight in this talk about how do we sustain study in the hard sciences.
I appreciate the comments. Maybe we'll just go down. I'll give each speaker 1 minute to respond, because you've just, I think, opened a very large conversation. But Anna, do you want to start?
Maybe he starts.
Okay, we'll start with Ollie. 1 minute, I'm timing you.
All right. For me, it all belongs together. I don't think that science can be there without art, and art can be there without science. I think that an artist mind can lift me personally as a very rational person. And also my education is not only based on scientific fact, it's also knowing the arts, knowing music. And if you look at nature, nature is a lot about symmetry. It's a lot about really beauty in nature. And if you try to find beauty in nature on a scientific way, you really connect everything. So I appreciate that we need to be conscious of scientific progress and scientific thinking, critical thinking, but I think art belongs to that as well.
Thank you. Brian?
I read a lot of comic books as a kid, a lot. And I think part of that experience is what has, I can draw very close connections to the stories that I read and some of the science that I do now, not in doing the equations or writing the code, but in some of the creative leaps that I've made to make new discoveries. So while I do think that we as a society would do better to value more immediately or more clearly how science impacts our lives, I don't think that it needs to come at the expense of non-STEM activities. And I agree with you that there is something fundamental here, and I think it's not that we spent a whole bunch of time talking about money. We didn't get to this issue. We got to this issue because you brought it up and because we were getting to that point. And I think these are important conversations to have. And I think that there is a fundamentality that we should be thinking about in terms of the critical thinking and the creativity that are enabled by a diverse kind of education.
So I think it's time to adjourn at least the formal session of this meeting, and I would invite us to continue this conversation about the role of culture and where that comes from and how that influences what we talked about tonight. So I want to thank our hosts and our sponsors, the Chicago Culture for Science and Technology. That was a light joke. But I think we really do live in an area that does have an opportunity and a tradition of caring about discovery and advancing the human condition. So thank you all for coming. I think we'll have a few minutes to mingle afterwards, and at some point the library may actually have to close. But thank you everyone for coming tonight, and thanks again to our sponsors.
Thank you.